Right. Now, what we're going to look at today, we're going to move away from the mechanics stuff for a little bit and go back to materials, because part of what you do with this civil structures is you start to look at the applications of some of the materials we've looked at in the past and introduce you to one or two new ones, and in particular concrete. So we'll be looking at that towards the end of what I talk about now. There's also going to be some videos that I've just sort of cobbled together from YouTube. There's 3 rather good ones that I found, and I've just put them together as one long 20-minute video you can watch online after this. So you can go to that afterwards. Now, when we are looking at civil structures, as we said in the beginning of this, is you're looking at things that are on a larger scale than, say, a personal or private use, and it's going to be a public use material. And there's a whole range of things here. You could look at roads as asphalt. You can look at houses in particular, like their civil structures as well. They'd be mainly timber. When you think about bridges, you probably start to recognise that there's probably only 3 types of materials that bridges are made of that you notice. And they would be stone, particularly old-fashioned ones, cut stone, wood, perhaps. Not many wood bridges around anymore. I mean, that one at Palmer Road that was just recently removed is probably one of the last ones around here that you'll find. There are a lot out west still, a lot in country towns and things, because they basically don't have the transport and don't have the sorts of level of usage that would require them to be much stronger. But we're phasing out timber use for bridge building and truss building. It has been that way for a fairly long time. Steel, right? So the steel bridges, just think about, in a couple of weeks' time we're going to go for an excursion, which, we don't do too many excursions in the course, but one of them is just to walk down the road and see the bridges. We've got a couple of good ones down there to have a look at. And next to it, so you've got the steel one, and next to it you've got the concrete one. And you can pretty much track time over the use of materials on these things. Timber bridges certainly were the earliest types, perhaps. We talked about this at the beginning. Perhaps a suspension bridge using rope might have been also in amongst that. Not many timber bridges survive that long that we can say that was what everybody used. So we get this impression, when you look back at things, the only things still standing tend to be those made of stone. So we have this impression that all the bridges in the past must have been made of stone. Possibly not. Timber would have probably been just as common to use, because timber was readily available. So you wouldn't be cutting stone if you didn't have to. If it had high traffic, like the Romans tended to have a lot more people using the roads and developing road systems for that purpose. One of the reasons why the Romans liked to have the road surfaces working so well was that they could control everybody that way. If you could get your army to be somewhere very quickly, then that particular thing was a deterrent to misbehaviour within regions. So within a league or within a certain distance, they knew they could march in a day. So they positioned their troops so that they could be somewhere very quickly, and the roads were surfaced so that they could do that. So bridges there might have had some purpose and importance. But your side streets, your back alley streets, or the general roads that people would walk on, probably just wooden bridges most of the time. Okay, so those are the basic materials you're used to. As you get later in time, we started to understand more about things like steel. Steel was a fairly late comer in terms of, like building materials over time. The ancient buildings don't have too much steel in them, if any at all. Or they might have some iron in places, because iron was known, but they might have them as nails or some sort of fixing device. But in general, you're not going to see too much steel in these buildings. You will see a lot of cut stone. Some of the Roman buildings, though, had this unique new material, this cement. And often you would use a combination of materials, even the Egyptians were doing this, with a mortar, which was just a material that would, and we'll explain the chemistry of it in a little bit, was used to bind together the rocks, if you were using rocks. Maybe you made clay sort of bricks with straw, and you wanted them to be weatherproof and hold together, so you'd make up a mortar. And what they discovered was a material, limestone, calcium carbonate, which is the result of dead organisms, basically shell material over time in ancient oceans, falling to the base of the ocean, depositing out in their own weight. The masses would be enough to cover it and squeeze it, and it would turn into a material rock, and we call it limestone for a reason. the lime that you get from limestone is you take the calcium carbonate and you cook it, burn it, heat it up. And if you do that, the calcium carbonate, calcium and CO3, calcium carbonate, the carbon and the oxygens combine to form CO2, which is released in that heating process, leaving behind C, calcium, A, oxygen, CaO. That's lime. Now, lime has a particular property, and that property is that if you put it with water, or at least make it wet, you can mold it, you can use it as a powder, but you can also mold it. And when it reacts with the carbon dioxide in the atmosphere, it can revert back to a solid form. So you've driven carbon dioxide off, and also if you put it in the presence of silica dioxide, sand, just silica. So if you put it in the presence of that, the combination of the silica dioxide and the calcium oxide, the lime, produces a gel-like property between the material when it's wet, when you add water to it. And that will make it go hard over time. We'll talk about that in a minute, but basically it's a really unique material. And the Romans spotted this because they were very good, the Romans, at seeing what other people were doing around the place, and the Egyptian had noticed this as well. But what you needed was you needed an environment where naturally calcium carbonate, limestone, was somehow going to be heated enough. Temperatures in the order of about 1450 degrees Celsius. That's hot. You don't get those just by lighting a fire and blowing on it as hard as you can. The only places that tended to produce those sorts of heats that were naturally occurring were around volcanoes, vents in volcanoes. And throughout the Mediterranean, particularly, the big one, Vesuvius, and if you have a deposit of limestone, or you have a deposit of calcium carbonate, we call it limestone because of the lime, and it gets heated up naturally by one of these vents, or in a volcanic reaction of some form. There might have been a flow of lava going past. The other thing that the Romans noticed too is when that same stuff hit beaches, it had run down onto the beaches, it affected the silica in the silica dioxide, and it formed glasses. So we sort of, in just observing things, now glass had been around for a lot longer than the Romans. The Greeks were using it, the Phoenicians were trading in it, but the idea of where did it come from in the first place is possibly out of observation of natural occurrence, or even in the process of making clay pots, and you notice that if you heat the silica up and it will put sand into a furnace that you're using to dry out a pot, you might find that it runs into a glassy phase. I did mention once before that may also have been the place in which we discovered metals and how to remove the oxygen from an oxide of metal to form the pure metal. So there's a little bit of conjecture about it, but it's logical. It's going to be found in these places, naturally occurring, or observing what happens in another situation that you weren't expecting it to take place. But here's the big deal. They noticed that if you got this material that had been heated, limestone, calcium carbonate, had been affected by heat, crushed it up and powdered it, added it with sand, then wet it all up, and then left it, it started to go hard. And it hardened up over time. The interesting thing about it is, and this is something you might notice, when you see a cement truck, what's a cement truck doing? Apart from driving cement around, it's cement mixing, it's moving. It's actually quite important because the kind of materials that they make now, Portland cement in particular, when you add it all together and put your aggregate and concrete together so that it becomes a concrete, we'll talk about that again in a second. So you've got sand, cement and aggregate, which is basically just crushed stone, and you don't want it to set in the back of the truck. You keep it moving because it's the movement that stops the gel forming around the materials and making it go hard. So once you've poured it, and you can have rapid set concrete, you can have lime that's called quick lime, and it basically, if you get it wet and you get it wet at all, within 30 minutes, some even 10 minutes. There's a whole lot of science going into how the setting process goes off with concretes. There's a couple called 2-pack. Have you heard of that? Used a lot where you put two types of materials that actually react very quickly. And you may be making a post hole, and you want that post to go into the ground and go off really quickly. You drill your post hole, you drop in the two components, the 2-pack components, it's basically a cement mix. Then you put your post in, and as you put the post in, you can actually bolt the post in, which will break and damage the two components, ram them together. The shock loading of that will impart energy into it, and that will then go off hard really quickly. So often used in mining, and when you put the supports up into the walls, they drill a hole into the wall, put a 2-pack mixture in, jam in fire it in actually, they ram it in hydraulically, some sort of bolt that then allows you to attach things to the outside of that and locks tight. So you can shore up the roof of a mine and other places like that. So anyway, let's just revisit then the materials that are important to us in this area and as we've been talking about beams, we'll come back and look at what a beam structure looks like when we actually put these things together. The two materials that come late to the scene that are important to us are going to be your steels, and steel particularly in two forms, in the form of rod and in the form of cable. So it's drawn wire that's formed into cable. Now there would be another way you could build a civil structure out of steel that supports load. You could make it into chain, and the chain could be supportive of load, and you could hang chain and allow a bridge or something to be made that way. It's not likely to be used because there's a couple of problems with that process, but generally speaking for us today, these are the main things. The rod becomes part of the reinforcement. Now reinforcement basically is making something stronger for a reason by creating a composite material. Now we've talked about composite materials before. So a composite material really is simply a combination of two or more materials with the direct purpose of improving one or all of them. So there might be a weakness in one material that can be improved by the addition of another material. And when we were looking at this earlier on, one of the things I mentioned was, say, fiberglass, where you wouldn't think you'd make a boat out of glass. But if you make it into fibers and then add resin to it, the shaping process makes it really easy. And the strength comes from, well, it's a combination of the strength. You're going to get the resilience that comes from the fact that the polymers can flex and bend, and you've got the rigidity and stability and stabilizing effect of the glass fibers. So you're combining two materials to get a better result. So the other one is cement, which is the thing I've just been talking about. Cement becomes concrete only when you add, so you turn it into concrete, which is a different word altogether obviously, by virtue of adding sand, the cement and the sand, and some sort of aggregate. Now aggregate really is there to do two things. It creates a binding effect as well, and it's usually a hard rock, say a blue metal, dolomite material, one of the harder rocks. The sand, if you just use sand and cement, you can make concrete. A lot of paving is just done that way because it doesn't need the aggregate because the strength requirements are not that high. But aggregate can help bulk it out. So you're not using as much of the cement and the sand, you bulk it out with the materials. You can often throw in old broken pots and things as well. So a lot of concreters will break up old rocks. Old concrete even gets thrown in as the aggregate for new concrete. It's a good way of maintaining and reusing and recycling. So the cement is really the binding agent. It is in the group of cermets, and a cermet basically is one of those materials that is mainly ionically bonded and with some covalent bonding. If it's really a very strong directional bonding. It's all the rocks and the sands and all those materials fit into the cermet group. They're not metals. Metals, of course, have that covalent bond that has the time fluctuating nature that allows it to be a bit more non-directional, but it's more about the packing and arrangement. Gives you better things for particularly in deformation situations. These guys don't like deformation very much. They're very good in compression, pretty ordinary when you start loading them in tension, which is why these two together are important for our building purposes. Because when we combine our cement and our steel in the right ways, in our concrete and steel, we can start to use them in ways that really we'd never dreamed of doing up until 150 years ago, perhaps. So while steel was being improved throughout the 1800s, the qualities of steels were going up, the control of steels, the science of steels, the chemistry behind it, the ability to understand what was actually taking place in steel mixes. And when you add alloys of other materials, the effects of those, creating things like stainless steels and creating different types of casting steels. So that sort of knowledge that started to develop after the 1700s, the Industrial Revolution, particularly in Britain, and then through the 1800s and the early 1900s, steel was the big new material. Cement needed to be improved on what the Romans used and what was known about lime and lime mortar and the sort of bonding agents they used just for brickwork. And it became an interesting exercise for a particular scientist in England, and he comes up with the particular material we now know as Portland cement. And when he finds this nature of being able to make it fluid, mixable, and so it won't go off, if you keep it moving, it doesn't go off until you actually let it sit for a while. And the good thing about cement is that it actually gets harder over time. The longer you leave it, the harder it becomes. And you can control the rate at which it goes off by the mixtures and the type of cements. Basically, the cement is made up of 4 oxides. Silica oxide, aluminium oxide, what's the other one? Iron oxide, silly me. So those 3 oxides are combined together with the calcium oxide, that's the CaO, which is the lime. The lime dominates. Most cement mixes are going to have something like more than 50, maybe 60% of the mixture is going to be made up of the calcium oxide. The rest, the other oxides, the silica oxides, the aluminium oxides and the iron oxides are there. And that's why cement has that sort of grey colour, not white. Limestone, think of the cliffs of Dover. Yeah, big cliffs, white cliffs of Dover. That's the limestone. When you crush it up, you'd think you get white. In the case of cement, what you're doing is adding other things. Aluminium and iron will create a slightly darker colour. So it comes out looking slightly grey. Right? And the way in which that's made and the mixtures and the combinations will make a difference to how fast and how quickly or what sort of strength you have at the end of the mix and so on. So you get a little bit of chemistry in there. Thankfully, you guys don't have to know that. You could go into a career just in making cement. There is a downside to cement though. You probably hear about it in the news. Obviously, if I'm taking calcium carbonate and I'm driving off carbon and oxygen into the air as CO2, I'm not doing a whole lot to help the situation about greenhouse gases. So of the materials we currently make, steel is pretty ordinary too, production steel, but we can improve that. We get that down to minor levels and they can control that. But making cement is probably in amongst, if not the most carbon greenhouse gas unfriendly type of material. The other side of it is there's a whole lot of carbon, a whole lot of limestone out there, so you're probably never going to run out of the stuff. Yeah.
What does it let off? It's bad.
Carbon dioxide.
How can you destroy that?
No, carbon dioxide is part of the atmosphere now. Well, you can trap it. As you've been listening to the news, they talk about trapping. The best carbon trap of all is a tree. So by planting trees, you're pulling carbon dioxide back out of the air. But the calcium carbonate it's a bit like all fossil fuels were created in situations that are no longer around. So you're digging something out of the ground that has been manufactured or created by situations that were 2, 3, 4 million years, if not longer ago. You're squashing down whole rainforests that were alive. So all the carbon that was in the rainforest being squashed down and combined driving out water and other things over time, forming coal. We dig this back up. Now, millions of years ago, when the trees were growing, they were ripping the carbon out of the atmosphere. We burn it. What we've done is just shove that carbon back into the atmosphere. So if we don't start pulling it back out with trees, and the other one is that they think, there's certain chemicals that have an affinity to carbon dioxide that you can pull into a rock or a material, and then you can transport that to the middle of a desert, like in the middle of Australia somewhere or anywhere, and you bury it. So basically you're just repeating the cycle. So there's got to be better ways than that, and that's what the arguments are around at the moment about reducing carbon content in the atmosphere. Yeah, we could fire it out into space, I suppose, but it'd probably cost so much to do that, it'd probably be better to come up with an alternative. Anyway, just be aware that cement, I'm going to be talking about it like it's fantastic building material, but it's always been a fairly high pollutant material as well. And eventually we will have to start thinking about how we change that. So for the purposes, the future's going to make it possible, make it both possible and mandatory. So anyway. Right, where was I going? Cement and steel combined together gives you something known as, clearly, from the words we've got up there, reinforced concrete. So reinforced concrete is steel and cement as its concrete form. Why do we put the reinforcement in? We know that this is a cermet, which means that it's not very strong in tension. In compression, fine. So if I'm building big, say stone bridges, and I just want the cement to hold it together, the load coming from the stone will be okay. It'll still crack if it gets some sideways motions on it or any tension load on it, so you'll see the cracks in the mortar. But generally speaking, if you keep it compressed, it's fine. Yeah. All right, what are we generally building? Well, look, just think about the bridge down the bottom here. Right? The steel bridge is a truss bridge. And remember that at the moment we've been looking at beams, structures of beams. And I've been keeping it really simple, the beam being just some sort of uniform material. And we started talking about wood as the basic one. In one of the little diagrams I was doing online, I did this. I put a little bit of V through it to show that it could be made up of trusses interior to it. Still be called a beam. It's simply supporting two ends, which really is a very thin truss. So if you think about the material within it being a thin truss. But here's the big deal. The problem is when we load it, we're going to have deformation. Why do we have deformation? We have to have deformation. Without deformation, you don't get resistance. If you don't get resistance, it doesn't hold the load, in which case it's a very useless piece of material as a beam. We don't want it to break, we want it to bend. And the more it bends, the less likely it is to be useful either. So we want it to have some stiffness, which is good, but we also need it to deform, to get that reaction that'll hold the load. But the deformation creates this situation. I'm exaggerating this, of course, because you will not get that much of a bend in it, because if you did, could you imagine a bridge, driving over a bridge which flexed like that as you drove across? You'd have to drive the car uphill to get out of the bridge. You'd probably roll backwards and forwards into the centre. But that's an effect. And what has happened, if you look at it in terms of an axis running through the middle, the top chord, that's the curved surface, or the top sector of the chord of the circle there, the arc, has shortened relative to the length of the middle part. This part here is shorter than the middle of the material, or a point in the middle of the material, a neutral axis. On the outside, it has stretched. I'll just put some arrows to sort of indicate that. Right. It is stretching on the outside. Fair enough? All right. Now, in the main, that's not a big deal. In fact, if we used something like timber for that, which is what we may have used a long time ago for a beam for a bridge, we just lay a piece of timber down, put 3 or 4 of them together, lay some planks across it, and you're good to go. I mentioned this at the beginning too. What's the big issue with that? Why don't we still do that? There's a couple of reasons, but one of the major one is trees are only so long. Somewhere along the line you're going to have to join the trees together, and the tree join parts become the weak element. So you don't tend to make really huge bridges out of timber anymore. And you have to increase the number of trusses and strengthening devices because timber still has limits. Certainly isn't as strong as steel. So it's bending. Timber is good at that. Why? Just think about it. What is that? What's a tree when it's a tree? Why is a tree and why is it tree-shaped? A tree is a long pole-like structure that generally bends due to the wind. It's anchored at the bottom and it will bend and flex. So its own nature as a tree has developed mechanisms within it to do exactly what we want it to do when we apply it to a beam structure. Which is why timber still gets used in certain applications for that very reason. So in minor applications, houses, roof trusses, those sorts of things, absolutely perfect. Cheap, reasonably easy to replace, and does the job. It's when it gets long that it becomes an issue. We just run out of big trees. So we started replacing things with. The other one was to do the arch type thing, which was the stone one. But again, you've got limits to how far you can go with that, because the arch height is going to have some determination on the width, so you can get the strength. So unless you want a really tall bridge to get over a really big river, you're probably going to have to do it in little jumps. And if you have to do it in little jumps, that means that part of the material has to be in the water, and that could be a point of weakness or a problem during flooding, or if there's rubbish coming down the river, it hits those sections. A lot of places, we don't seem to have the issue here because we just don't think of it. But in a lot of northern European countries, the biggest problem to a bridge is ice. A lot of bridges in Russia and through Norway and Scandinavia, when the winter comes and the ice forms, and later when it starts to break up, you can have flows of ice coming down and ramming up against the bridges. It's fairly solid, it's not flexible, it's not going to flow around, it's going to back up and cause problems. So there's a few things about those types of structures that limit how far we can go, which is why we now tend to have steel as an option and concrete. But concrete has a problem. It's to do with that bottom surface. Let me just get these things out of the road. Maybe you can take that out now because we don't need that. So we've got let's say we make a concrete beam. We've cast it out, we put a couple of pieces of wood down the side of formwork, we pour the concrete in, we know that we can, if we keep it moving, we can make it all reasonable. So we bang the sides of it, pop it up and down to get the air out, that sort of stuff, agitate it, then you say, right, it's ready, leave it. So now we've got this beam of concrete we've created, big block of concrete, and we do the job of putting it onto two ends to support, and then we load it. And what we find, of course, is it does exactly what we'd expect it to do. It deflects, bends, has to, gives us that support. But now what's happening is this bottom section is stretching, and with ceramics, rocks, or any of these, even glass, which fits into the scheme of things, if there's a crack in the surface, and you won't get every surface to be perfect. So if there's a crack in the surface, that crack, I'm exaggerating them here, becomes a problem for the load because there's no material for the load across. So that material here is being stretched, but there's nothing holding the two together. So that's not where the load is. The load can't be shared across that section because there's a gap there. So what the load has to do is it has to go up and over the cracks. And the one above that, the loading in the material above that, goes up and over the crack. And the one above that goes up and over the crack, and it bunches up in this point above the crack. It's actually known as a stress raiser. It rises the stress or concentrates the stress at the tip of the crack. Does that make sense? It should do, because you can't go through the gap. So the material is actually thinner at those crack points. And that causes a whole bunch of other issues for us. So as we get to that place where the stress in that, tension stress, starts to get large, the crack, as you pull it apart, the stress razor here cracks it even further. And that crack, it's known as crack propagation, that crack gets more and more stress concentration at the top as you get wider and wider. So eventually what happens, you reach a point where you are overloading the material and what's left in thickness above can't handle the load. It fails. It fails in tension because the cracks open up, forcing the load to the tops of the cracks and making a crack concentrator. What about the cracks on the top? Because I said there's cracks in the surface, you can't really make one without some form of problem in the surface. No surface is dead flat and perfect. You can try really hard. So what do you think is going to happen? Why would they spread? They're spreading down here. What are the guys at the top doing? They're closing. So now the surfaces of the crack are actually leaning on each other, and so the stress can be transferred directly across the crack. Hence, these types of materials have strength in compression, but not in tension. Because the tension is opening the cracks up and making stress razors. The cracks in compression are being closed, and it's just like saying, well, I had two bricks and I could have a completely cut straight across there. That's a large crack. It's just completely cut. Leaning on each other, it's going to be fine. As long as it's compression, it's going to be fine. I don't really have to worry about it. But the moment I start loading it in tension, they're just going to fall apart because they're obviously not connected anyway. Should make sense, should be perfectly logical. So, that limits how we can use our concrete beam. The further you go, the longer the beam, the more pronounced the curve, the bigger the arc, the more open the cracks, the more likely it is to fail. So now we're back to timber was a problem because it was limited in length because trees aren't too tall. Now we find ourselves limited in how far we can go with concrete. Because if we go too far, and concrete is heavy. I mean, you put aggregate into there, you've got sand, you've got the cement, its weight alone could be enough to make it break. It's quite possible that you could make a beam out of pure concrete or pure cement and just have it sit between two things and its own weight will crack it. You don't even have to load it, it'll just fall apart in front of you. I mean, obviously getting it to that position and holding it until you take something out would be a tricky thing to do, but its own weight becomes a problem for itself. So how do we fix it? How do we go about trying to fix it? This is where the reinforcement comes in. What's steel good at compared to this? Tension, good. Steel can be made to resist tension by deforming. Why does it have good tension capability? Go back to one of these diagrams that we've looked at. What's this one called? Load extension diagram or the stress strain diagram. Right? That gives me something about this range. What is that range? The yield's there, that's the yield point, but that range here, the material, it's the elastic range, which means that I can load it and load it and load it. As long as I don't exceed the yield, I can take the load off and it will return. Steel is great to have that range. It's really good for that. You can even have it so that it does a little bit of yielding and it's still okay in situations and you're all right, because what it won't do is, not like a ceramic, it doesn't just go straight up and crack on you. So there's some support mechanism there even after you've made it go further than you really want to. But it's this elastic nature that makes the steel useful in tension, because it will return, tries to pull back all the time, and it pulls back to fairly high loads. So that's good. So what we do is we say, let's put some steel, which is good in tension, into a material that is weak in tension. Now the question is, Where should we put it? Here is a side view of my concrete block. I know that the weakest point, if I say here's the middle axis, the neutral axis, it's the one that doesn't change in length. All right, that doesn't change, so it's going to be fine just as it is. Everything above that, this range up here, is going to be shorter when it's deflecting. So all of this region up here will be in compression. So basically that we don't have to worry about. It's going to have more compression at the top than here, and here as well, because it's neutral. There won't be any value to that if that's the neutral axis, has the term neutral, nothing going on. Below that neutral axis, we increase our tension. Where is the most tension? At the bottom, the further away. And if we make the beam larger, then that distance is further, which means the tension is higher at the bottom if you deepen your beam. So now we have to think through, where will we put our steel? We want our steel to be in a place towards the bottom where the tension is at its most, so we can keep the thing from cracking open. And even if it does crack, the steel's going to hold it together, so that that crack propagation, the stretching, say there's a steel beam going through this section here, the crack gets up to the steel, and the steel then holds the material. And you never go, you might crack a little bit past it, but you really don't create major stress levels above. So it stops the propagation of the crack through the material as well. Making sense? All right. If it does, you might notice something else that happens when you build a house. There's a house building technique which is to put a concrete slab down on the ground and build on that. Gives you a nice flat stable area. And the shape of the slab is a bit like that. Just hang in there for a minute, I'll finish off. This sort of slab is called a raft slab because it sits slightly off to the ground on a builded mound of dirt. So it's a big flat area like this. Where would you put the concrete, put the reinforcement this time? They tend to put it towards the top, because the loading comes from the beams or from the roof trusses and down through the studs onto these. The footings hold it in and stop it from moving, and they will put reinforcement into here as well to keep that bound together. But what's happening to the raft is it wants to bend that way with the loading coming down on the side. So in these types of structures, you put it towards the top. And you may notice when you see people pouring concrete, they put these little foot things, little metal foots and plates and little cup sort of things to sit the reinforcement on to raise it up into the material. Now there's something else we can do that is really cool. This is when you're just casting the concrete. This is just pouring concrete around mesh. You put the mesh in. One of the videos shows a building site where they're putting the mesh into it, into a big container. You pour the concrete into that, you let it set, and it's good to hold together. But we can actually improve that more by doing something called tensioning, pre and post tensioned reinforced steel. We're going to leave that one for another lesson, because that's enough to get your head around right now. And I would like you to have a look at the videos that go with the concrete, what is concrete and cement, and that one about how to build with it, and just the history of it. And the last part of that starts to introduce you to pre-tensioned, post-tensioned concrete. All right? Good.